The last video we talked about, all these scientists and philosophers here on the left, but we also talked about Max Planck and Albert Einstein. Max Planck introduced the idea that energy from light is quantized and it can be described as quanta, per se, of these discrete packets of energy. And Albert Einstein took Max Planck's idea and in one of his papers in 1905, which he published, he talked about the photoelectric effect that used Max Planck's idea. So today we're going to see how exactly this idea of quantized energy really ties into the development of the atom. So let's start off with this gentleman right over here. His name is Ernest Rutherford. So Ernest Rutherford. You may recognize him from your previous chemistry studies. Why can't I write? Oh, there we go. Okay. Computer's bugging out. Always nice. So you may recognize him from your previous chemistry studies. And basically, he did something called the gold foil experiment. So what he did was basically he shot alpha particles through a very, very thin gold foil sheet. And according to J.J. Thomson's model, which is this jelly with positive jelly with electrons scattered around. This experiment was either going to verify or contradict J.J. Thomson's model, and it contradicted it. So in what was supposed to happen, so I'll do green and supposed to happen, what's supposed to happen was that many of these alpha particles were supposed to go through, and some minor deflections, and the angle was going to be very small, so theta would be small per se. Right? They'd be small. I'll just get rid of this guy here. So they were supposed to be small and the reason they're supposed to be small is maybe occasionally, the alpha particle may collide with an electron here and then bounce off like this or this, right? So that was expected, just minor collisions. What actually happened, and I'm going to do this in blue, what actually happened was that the angles of collision, quite a few that collided were greater than 90 degrees. So theta, so 90 degrees, greater than or equal to 90 degrees. A lot of the collisions were greater than 90 degrees. And that really shocked Rutherford. And he has this famous quote of, I actually forgot it. But, basically what was really happening was that, we know now that there's a proton in the center. And so when all these alpha particles were going through this very thin gold foil sheet, a lot of them were, hitting right, I'll do this in blue. We're hitting the proton right here. And so that was going to have a massive collision. And so the angle was bound to be greater than 90 degrees in that case because there's a very dense nucleus here. This is very dense. This is the only place where the proton will be found, right in the center of the atom. So that's how Ernest Rutherford discovered it. And he did through math. He had this little thing in the back that could detect where the collisions happen, like here, here, here. He did many trials, he calculated the data and came up to the conclusion that, the proton has to be in the center. And so that contradicted J.J. Thomson's model, but it is more correct. So this model was basically called, I'll just erase this here. You may recall that this model is called the planetary / nuclear model. And that's mainly because the idea was that this electron is orbiting around. But the problem with Ernest Rutherford's model, and he even knew it was limited, was that there was nothing stopping the proton and the electron from meeting. So it was sort of unstable. So that was one of the limitations, the idea that, not only is it a 2D orbit in a three-dimensional world, it's also nothing stopping this electron from this proton to meeting. So eventually it would collide and then, explode. So we know that, atoms just not, normal atoms aren't unstable. So this was a limitation, but it gave a better sense of what the positive charge is in an atom that's in the center. And that's because, again, the collisions were greater than 90 degrees due to many of the alpha particles colliding right in the center of the nucleus rather than, in this uniform positive jelly where it hits an electron here or there. So that's Ernest Rutherford. Then comes Bohr. So Niels Bohr. He basically took what Albert Einstein talked about in the photoelectric effect and this idea of a photon being able to trap, sort of transfer its energy to the electron, and if it has enough energy to take the electron out of its place, then it can shoot it up. So he basically thought, well, what if electrons exist in quantized energy levels? What if, right, you have your proton center here, and then you had these quantized energy levels. So the farther you were away from the proton, the greater energy you had. And he played around with hydrogen a lot. Hydrogen was his favorite thing, I guess. And so he basically did a lot of math, and he was able to prove mathematically with this idea that, let's say if you had an electron chilling here, I'll just represent it by this yellow circle. And let's say a very high energy photon. Let's see if I have do I have a purple? I do. To, show a higher energy. Let's say you had a photon coming like this, right? If it hit this, it would transfer all its energy and it would go to a higher energy level. So this would bounce up here. And we can see that in the absorption spectrum. So if you look right here, that's about 400 nanometers, right? I'm just, I'm sure I don't have the exact color, but that's the idea. So you can see in the absorption spectrum that, okay, something absorbs energy, so it moves to a higher energy level. So this is n equals 1, n equals 2. This third one is n equals 3. The fourth one's n equals 4. These are different shells, right? So basically it absorbs this energy and then it goes up to here. And then after a while, it'll come back down and release that energy. And we can see that in the emission spectrum right over here. So that's basically the idea of the Bohr model. And you can see it's very similar to the photoelectric effect in the sense that it's absorbing energy, except you're not shooting the electron off and making it into a photoelectron. The idea Bohr just had was like, well, basically this electron could absorb that energy, that packet of energy, to move it to a energy state. If you let's say had some red wavelength, so I'll draw another electron on the side here. Oh, no, not there. Let's say I drew it right close to here. And then, it's my pink. And then I had a lower energy thing, photon attack this. Then maybe it can move up only just to 1, and it just moves up on this one, right? So it just elevates to N2, and then that can be seen in the emission spectrum as well. So the emission spectrum is what it radiates outwards, so it's returning back to its ground state. The absorption spectrum is it's moving up to its elevated state because it's interactive with light. So that was basically the Bohr model, and so his whole idea was, and I can write it down here, is that electrons exist in quantized energy levels. And that's basically it. Now, while his model was great, the problem was it couldn't explain things very well for atoms that had more than 2 electrons. And we're going to get into that specifically as to why, and we'll see with Schrodinger. But basically, since he experimented only so much with hydrogen, it was good for hydrogen for sure. I mean, this is a big step, but we're going to notice something later on as we understand this unit, is that Bohr was only working with 1 quantum number. And that may not make any sense to you, but just keep it in mind. You'll understand that later on. So Bohr was only working with 1 quantum number. And I just want you to keep this in mind, because you're going to learn about quantum numbers real soon in this unit, and everything will just click. It'll be full circle. Anyway, so that's basically it. The idea that electrons exist in these quantized energy levels, and based on the photon that interacts with these electrons, they can jump to higher states of energy or lower states of not like a little bit higher or more higher, and then come back down. And that's proven by the hydrogen spectrum as seen in the emission and the absorption. Next guy we have is Louis de Broglie. I am very bad with French, forgive me, but I'm gonna call him de Broglie. Yeah. So basically, he thought, well, if light has, and I apologize, I didn't mention this before. I should have mentioned this, but basically, if you notice the way I've been doing my drawings, all these photons, this purple one or this red one, I've been drawing them as a wave and as a photon, and that's because light acts as a wave and a particle. It's called a wave-particle duality, and it's been proven, through physics and all that stuff. I think I didn't mention it. If I already mentioned it, then I just forgot. But basically, by this point, by the time, Planck was around, it was proven that light has both wave and a particle characteristic, which is really hard to imagine. But then again, things at the quantum scale don't really make sense, aren't really easy to imagine. But anyways, so what Louis de Broglie thought was, well, if light can exhibit particle and wave characteristics, then matter, which has particle characteristics, could also experience wave characteristics. So his whole idea was that, I'll write it down, if light can do both, then matter can do both. So basically, what his model of the atom looked like was, or no, not a circle, was this idea that, well, all pieces of matter have waves. So if light can be both a particle and a wave, then matter can also be both particle and a wave. So we see that basically he just took Bohr's idea, this Bohr-Rutherford diagram, and he just gave it waves. And he came up with an equation. I'm getting a little physics-y here, but I think including this helps to understand. Where wavelength equals to Planck's constant, divided by the mass times the velocity of the particle. And you can actually calculate your own wavelength. I forgot the exact units for Planck's constant, you can search it up, but you can actually calculate your wavelength. And it's, incredibly tiny, but let's say, for example, a 60, if a 60 kilograms, so if M equals 60 kilograms, and they were running at 10 meters per second, and I forgot the units but I know it's 6.626 times. Did I forget the exponent as well? I did. Okay, forgive me. I forgot in Planck's constant. You can just search it up. Quick Google search. Don't worry about it. Anyways, if you actually did the math and you said, okay, what is the wavelength that a person of 60 kilograms running at 10 meters per second emitting? And if you use Planck's constant, you can actually find that their wavelength is 1.1 times 10 to the negative 36 meters. So that's incredibly small. 10 to the negative 36 meters, that's incredibly small. So if you were wondering perhaps, wait, so if all matter has wavelengths, then how come we can't see, how come we don't notice this? It's because since our mass is so big, right, compared to, because I think this is like negative something, it's huge. I think it's 36. I'll put it in the description what Planck's constant is. But basically, since our mass is so big, right, our wavelength is basically completely negligible. But when you get to the quantum scale, the mass is so tiny. I mean, I forgot all the values for the mass of the proton and electron. I'm very prepared, but the mass of the proton and electron are incredibly tiny compared to, someone who has a mass of 60 kilograms, right? So our wavelengths are completely negligible on the macroscopic scale. But if we were to look at things that are quite tiny, like electrons, their wave characteristics are extremely important. And so, basically, Louis de Broglie applied this idea that, well, if light is both a wave and a particle, then matter is also a wave and a particle, and he did the math and he found very similar results to what Bohr did in terms of these electron, quantized energy levels. And so this pretty much led to this development of orbitals, this idea of orbitals. And we're going to see that with Schrödinger right now. So that was Lewis de Broglie. Basically, matter has both wave and particle characteristics, just like light. And de Broglie was able to prove it with math. And things with larger mass tend to have negligible wavelengths because they're incredibly tiny, whereas something as an electron, their mass is, incredibly tiny as well. So mathematically speaking, if you had, let's say, -36, the exponent divided by, I don't know, 10 to the negative 30, I guess, whatever, right? I forgot the values, right? Then it's the wavelength is actually going to be quite more significant. So that's basically the gist of Lewis de Broglie. Moving on to this guy, Erwin Schrödinger. So he basically addressed Bohr's limitations. Bohr's model could not explain anything, could not explain the spectrum for elements that had more than 2 electrons. So he basically hypothesized that, well, maybe that electrons exist in orbitals with different energy levels or subshells. So I'll write that down. Electrons are in orbitals with different energy levels or subshells. So you're going to see later on in this unit there's going to be different sort of shapes and orientations of possible electron distribution. So basically Erwin Schrödinger really went to town and did the math. And he basically came up with this idea that orbitals are basically mathematical wave functions. So orbitals are mathematical wave functions that give the probability of finding an electron. Probability finding electron. So basically, if we think about this, according to Schrödinger, let's say if this was our atom, this is our nucleus, or actually I shouldn't even be drawing like that. Basically, if this is our positive, this shaded area, represents the probability of finding the electron with math. And then eventually, I'm trying to make this look like a circle. I know it just looks like spaghetti or whatever, but basically, it's just the idea that, well, there's a probability of finding an electron and that there's subshells. So there's shells. So if you had a main shell, so if we think of the Bohr model, so example, Bohr model here, right? And, this is a shell. There's probably a subshell. Let me pick this with a different color. So orange represents, there might be a subshell here or another subshell that can explain this weird stuff going on with the absorption spectrums of these different elements. As you can see, many different bands are being taken and all that. So, and Schrödinger's model basically could explain all these things, and it's verified by the numerous lines in the line spectra. So these orbitals are basically also known as electron clouds because they look like a very dense cloud. And again, it just gives the probability of finding an electron. And this model is basically called the quantum mechanical model of the atom. So it's all about probability and the idea that you could probably find an electron. There's a figure that's thrown around that, that you can find the electron in this range like 90% of the time. So, definitely very good. And you'll see that Schrödinger's idea of this probability distribution is not only verified by the multiple line spectra, this idea that, they're in these quantized energy levels with also subshells, but, this probability distribution, but it's also verified by another scientist, or the Schrödinger's model. His name was Werner Heisenberg. Let me get the Heisenberg. Probably didn't get the spelling right. So he basically came up with this mathematical idea. All of these guys like math, by the way, if you didn't figure that out already. So what the hell does this mean? This is Schrödinger. Not Schrödinger. This is called the Heisenberg uncertainty principle. And basically, delta x, this triangle x, means the uncertainty in the position this delta p, which is for momentum, if you haven't taken grade 12 physics yet, is just mv, mass times velocity, and this delta p represents uncertainty in momentum. And then we know from previous, that's just Planck's constant. So I'm just going to say P's constant. I don't have space to write here, but that's just Planck's constant. That's pi, from math, the circle stuff. So basically he represented this, this inequality. And what it really means is that delta x is inversely proportional to delta p. So basically, as one variable increases, the other decreases, which means that the more you know about an electron's position, this is talking about the electron, the less you know about its momentum. And the more you know about its momentum, the less you know about its position. This is called the Heisenberg uncertainty principle. And it pretty much like coincides with Schrödinger's model of this probability distribution where you could probably find it. And I don't want to get too much more into the math. I've already done more math. Like you won't see this equation in your chemistry class, but I thought it was important to show you this idea of this proportionality where, so let me write this on this side actually. Position and how can I say all? I'll just say delta x is inversely proportional to delta p. So this is a basic mathematical idea that's really quite important in quantum mechanics and also understanding Schrödinger's model. And once again, it's just the more you know about one thing, the less you know about the other thing. So you can never know, I'll write this here, you can never know an electron's position and momentum at the same time. So again, the more you know about, let's say, delta x, the less you know about delta p. The more you know about delta p, the less you know about delta x. And that's basically how it works. Moving on to the last guy. This is going to be very quick. James Chadwick. He basically discovered the neutron. So finally, somebody found something to keep the model stable. Oh my god. I'll just write neutron. I'm tired. He found the neutron. And I believe he did it through, he shot like alpha particles at a surface. So he shot alpha particles and he calculated the energy that was released. So energy released. And I won't dive into the physics about that. I actually don't know myself. But that's basically it. He found the neutron. So finally, you know, there's some idea that, okay, now, you know, there's a proton here. There's also, you know, a neutron here. And then here's your, oh, sorry, that's not even the correct thing. What it would really be is it would be a probability distribution. So a shading inside to show that where the electron is most likely to be. And another thing I forgot to mention is I had mentioned earlier about Bohr was only working with one quantum number. Schrödinger's equation, when you solve it, he created this mathematical equation. When you solve it, you get all these other quantum numbers that describe the geometric location of where the electron may be. So again, this is now what we're getting into is very specific of, okay, how can you define where the electron is and all that stuff. And that's basically it. So just to recap from the beginning, because I know this part may have been a little bit more than the last part. Ernest Rutherford, so reason why his discoveries contradicted J.J. Thomson's idea was because it was anticipated that there would be minor deflections. You know, occasionally the alpha particles may collide into some of the electrons here in this plum pudding model, you know, and the angle should be less than, you know, 9 degrees, should be quite small, not too big. There should be minimal. But in his experiments with a gold foil experiment, he found many times the deflections were greater than 90 degrees, and he did the math looking at, you know, where it was landing and all that stuff. And he was able to figure out that, well, the proton, this positive charge must be in the center. And he had the planetary/nuclear model. It was unstable because there's nothing stopping like charges from meeting each other, and we know that can't be possible. Otherwise, everything would just explode and we wouldn't live, right? Because we're made of atoms ourselves. So he even knew that was wrong. And then Bohr sort of filled in the gaps. He took what Einstein said about the photoelectric effect and this idea of quantization from light, and he said that electrons exist in quantized energy levels, as I indicated, like N1, N2, N3, N4. And that idea that, well, if a photon meets an electron, it can excite it and push it to a higher energy state right here. And then after some time, it'll come back down and release that energy, as can be seen in the emission spectrum. Then Louis de Broglie basically said, well, if light can be both a particle and a wave, then matter should also have a particle and wave characteristics. He did the math and he was right. You can calculate this out for yourself. Lambda equals Planck's constant over mass times velocity. You know, find your own mass in kilograms, try this. You'll see that your wavelength is incredibly small, but we all emit wavelengths, which is quite fascinating. And, you know, again, his results, you know, this thing agrees with Bohr in terms of the math. And also we accept it, that, you know, with the waves. Agrees with Bohr. And then we move on to Schrödinger. Oops, did not mean to do that. Who basically went even more rigorous into the math. And then he said, you know, electrons exist in orbitals or have these subshells. And these orbitals are basically, you know, wave functions that give the probability of finding the electron. And what you're going to see later on in this unit is that there are many different kinds of orientations, you know, as to, you know, how and where this electron may be. So if you were to draw like, you know, XYZ coordinate, you know, there'd be like some things that look like a lotus leaf flower and stuff like that. I'm very bad at drawing them, but you'll see, you may remember from grade 11, you know, S, P, D, F orbitals, all that stuff. That's coming back very soon, and we go more in depth in it, so that's always fun. And so, yeah, he basically gave it a probability distribution. Then Werner Heisenberg, a year later, sort of supported Schrodinger with his uncertainty principle, the idea that, you can't know an electron's position and momentum at the same time. You either know one or the other, and that's it, and you know less about the other. And then finally, James Chadwick came in to sort of fit, I guess, the last piece of the puzzle, and that's introduce the neutron. And then after that, there's been numerous developments in quantum mechanics. But that's basically been it. This is the history, of the atomic model. A very messy board. I apologize. I realized I was writing over, scientists all the time. But yeah, hopefully this helped. And yeah, that's pretty much it.